So today we're going to start off with a little bit of a discussion about the circulatory system. The circulatory system can be thought of as kind of like the roads in a city. You've got a bunch of houses here, you've got roadways. The roadways are different sizes. Some of them are one direction, some of them are two lane, but each lane functions in one direction. The purpose of the roadways are to supply the houses with mail, milk, whatever, the materials that people would need to have in order to live in their houses. There's also roadways where waste material could be taken away from the houses, your back alleyways. Back in the old days, we used to have milk that got delivered at the back door, bread that was delivered, and that would be done through smaller roadways that ran in behind the houses. So the point to remember here, the point to keep in mind, is that roadways are one direction only, and in the case of the streets, it keeps the traffic flowing. If we compare the analogy, or use that analogy to compare it to a body, the cells would be like, the houses would be like the cells of the body. The roadways would be the circulatory system. Our circulatory system is one direction. Okay, it doesn't flow back and forth, it moves in one direction. And the point of the circulatory system is to drop materials off with the body cells and to pick the wastes up from those cells. Now, the circulatory system is made up of three main parts. We've got the heart, we've got blood vessels, and we've got blood that circulates through those blood vessels to provide the tissues with everything that they need. Some of the main functions, we already mentioned that it transports oxygen and nutrients to the tissues. Waste materials like carbon dioxide, other things like lactic acid that builds up in your muscles. When you're exercising and you don't have enough oxygen, those things get removed from the cells. And we can transport some other materials like hormones and other chemical messengers throughout the body. Some of these other things like distributing body heat and defense against disease, especially defense against the disease, we'll talk about a little bit later when we get into the immune system. One of the things we can measure when we get into our heart is the amount of blood that flows through our body. We call that the cardiac output. So how we calculate this is we take the volume of the blood pumped by the heart in 1 minute based on the stroke volume and the heart rate. Now you can quickly find your heart rate by taking your pulse. You can count for 15 seconds, count the number of beats, the pulse for 15 seconds, multiply that number by 4, and that would be your resting heart rate. Resting heart rate is typically about 80 beats per minute, roughly. Depending on whether you're more athletic or not, it could be above or below that. High performance athletes might be as low as 40 or 50 beats per minute, and your regular everyday couch potato would be probably in the 90 to 100 range. So if you take that number as your heart rate and you multiply it by your stroke volume, which is the volume of blood pumped out of the heart per beat, you'll be able to calculate the amount of blood found in your body. Since your body circulates its blood about once a minute, that's how we're able to calculate. Now, for different sized people, they'll have different stroke volumes. Men tend to have slightly larger stroke volumes than women, in that 70 to 80 milliliter range, women in the 60 to 70 milliliter range. So when you do the math, we would take the stroke volume, 70 milliliters per beat, we would take the number of beats per minute, your resting heart rate, and when we do the calculation, notice the conversions here, we'd be able to calculate that the average person has approximately 5 liters of blood in their body. Now, getting into the heart. This would be a picture of a regular mammalian heart, regular human heart. When we do our heart dissection, you'll see that the heart looks very similar, but the heart dissection you guys are going to do will be of a sheep's heart most likely, and it'll have fat that's all over the surface of it. So some of these blood vessels up here will be a little bit hard to tell, hard to distinguish. But what we can see with the heart is muscular organ. Okay, it's different than a skeletal muscle, where this muscle can't tire. Skeletal muscles like your biceps and your quadriceps, those tire, they fatigue after a while. This type of muscle doesn't fatigue. Hearts found smack dab right in the middle of your chest. It's about the size of your fist. And what we can kind of see from the outside, there's a line that runs down the middle here, a groove, that separates one chamber, two chambers. You've got another chamber up on the top here. It looks kind of like a little leaf sitting on top of the heart. And there's another one over on this side over here. there's some blood vessels. Blood vessel here, another vessel right here. This one's called the aorta. These ones are called these ones are called the vena cava, superior vena cava, inferior vena cava. And then you can barely make it out, but there's a vessel that goes here, and that's going to go underneath the aorta here. That'll go off towards the lungs. This is called the pulmonary artery. Now, all over the surface of the heart, there are these things called coronary arteries, and they actually go down into the muscle of the heart itself, and they basically feed the muscle of the heart with blood. The heart's a muscle, so it needs to be supplied with oxygen and nutrients to keep the tissues alive. This will be really important for you in Science 30. You'll need to know, first of all, the parts of the heart that are in blue, which designates blood that's poor in oxygen. We'll say that it's deoxygenated, and the parts of the heart that are red. And those parts would be high in oxygen concentration. We would just say that they're oxygenated. And the first thing I need you to notice is that one side of the heart here, the left side of the heart, is actually on the right-hand side of your diagram. That's not a typo. It's because if you were looking at this heart sitting in a patient's chest, this would be that patient's left side. This would be the patient's right side, right? So it's a mirror image. If you were looking at this on somebody sitting on the desk, face up on the desk in front of you, that would be their left hand over on this side of the page. This would be their right hand over here. So that's something that I would typically ask you to do on a test is put a little R at the top of the page, put a little L at the top of the page, and that'll help you to remember that the left is actually on the right side and vice versa. Now there are two atrium for your heart, two atria for your heart, singular atrium, the right atrium, the left atrium. The walls of the atria are pretty thin compared to the bottom chambers that we call ventricles, right ventricle and left ventricle. These are thicker, they're a little more muscular, and that's because these guys do the pumping. They're the ones that push the blood out of the heart off towards the body. Running down the middle of the heart is what we call a septum. Okay? It separates the deoxygenated blood from the oxygenated blood. In between the atria and the ventricle, there are valves. And in Science 30, you don't need to know the names of these valves. We call them the atrioventricular valve. In between an atria and a ventricle, there's another one over here, an AV valve. But as said, the curriculum just requires you guys to know the name valve. They're one-way valves, so they prevent the backflow of blood from a ventricle back up into an atrium. We also have a valve. We call these guys semilunar valves. Those are in between the ventricles that lead out into the arteries. Okay, so we've got atria, ventricles, right and left ones, a septum, valves that prevent the backflow of blood. Then we get into the blood vessels. So starting with the blood coming into the heart from the body, after it's returned from the body, after the blood has already dropped off all of its oxygen and nutrients, and it's picked up its waste, its carbon dioxide, it's going to come back to the heart oxygen poor. It'll have a lot of carbon dioxide in it, and it'll empty into this right atrium from the vena cava, the superior vena cava, which returns blood from the upper body and chest, upper chest, and then the inferior vena cava that returns blood to the right atrium from the lower body and the abdomen. That blood will move through the right ventricle, then it will move out through the pulmonary artery, and the pulmonary artery branches, part of the blood going off to the left lung, part of the blood going to the right lung, where now oxygenation is going to happen. Straight diffusion. Carbon dioxide that's in the blood will move into the lungs. Oxygen from the lungs, when you take a puff of air in, oxygen is coming in. That oxygen will diffuse into the blood, and then it'll return back to the heart through pulmonary veins. Some of them from the right side, some of them from the left. They'll return into the heart, into the left atrium. These two over here go along the back side of the heart and would empty into the atrium on the back side. Blood moves down into the left ventricle. Ventricle pumps, and blood goes out into the aorta, off to the rest of the body. Now it's oxygenated, so it's providing oxygen-rich blood to the body tissues. It also goes around the back side of the heart, and it'll continue on to the lower part of the body to provide oxygen. Now when the heart beats, It does so in two contractions, sort of a rhythmic contraction, simultaneous contractions, where both ventricles contract at the same time and both atria contract at the same time. You don't need to know, like Bio 20, the electrical nature of how this works with SA nodes. So Bio 20 guys, don't worry about all of that. Just understanding both atria contract at the same time and then both ventricles contract at the same time. There are names for these cycles. One of the phases of the heart cycle, when it's relaxing, is called diastole. Okay? When we get into blood pressure later on, we'll talk about diastolic blood pressure. The other stage of the heart cycle is called systole, and that's when blood is ejected out of the heart. That's when the ventricles contract and they force the blood out through the arteries, either the aorta or the pulmonary arteries. Now, with this animation of the heart, you're going to be able to see the chambers as they're contracting and relaxing. So notice your two atria at the top wind up contracting at the same time, and the ventricles contract at the same time. Blood's coming in to the right atrium, and then it pushes down through the AV valve or the valve down into the right ventricle. Right ventricle contracts, it goes through another valve out through the pulmonary artery off towards the lungs. Now, once oxygenation has happened in the lungs, it goes back in through the pulmonary veins into the left atrium, down through the valve, into the left ventricle, and then when the ventricle contracts, out through the other valve, we call a semilunar valve, which is going to take the blood off now through the aorta to the rest of the body.